let me thank the sponsors for this talk, Space Solar Power Institute and a bunch of other companies that we've worked with recently. And so the idea of space solar power, you have enough to kind of understand the basics of it now, because we've studied all these orbital mechanics and these spacecraft subsystems. But there's been this idea around since the late 60s. It was first started by a man named Peter Glaser. He got a patent. He said, let's put a bunch of solar cells in space and then beam the power down on a microwave link, collect it on the Earth. And if you did enough of that, you could tie it into the grid and provide a substantial amount of free, not free, but very low cost, non-polluting energy, no carbon emissions, all that stuff. No radiation, no radioactive waste, none of this bad things that we associate with the energy sources that we use on planet Earth at the moment. And of course, they did a study back in the 1970s. The NASA commissioned this big study. And I think part of it was to justify the space shuttle program and the idea of using reusable launch vehicles to help bring down the costs of launch at the time, which were exorbitant. They said, this is a good idea. The physics are sound, but the engineering is through the roof. Like, there's no way to make it economical. It's by four orders of magnitude from profitability in the 70s. But there's always been a community of researchers that have looked at this. And as the cost has gone down for solar cells, for launching, solar cells have gotten more efficient, launch costs have dropped, we're getting better at making smaller, more efficient satellites. Now we look at the numbers and we think, well, we're only about 1 or 2 orders of magnitude away from being feasible. And hasn't been that long ago that we did these studies. Many of the people that did those studies are still alive. And so there's this big rush. Let me go ahead and skip to the next slide to explain, and then I'll go back. There's been all these demonstrations over the years for the wireless power transfer. Now first, why are we interested in putting the solar cells in space? Why not just put them on the ground where it's easier?
You absorb a lot more?
You do absorb more. You get, the sun never sets in space, nor does it rain. And so you get about 1,360 watts per meter squared, regardless of what the weather is. That's important, because that means that if you can get that reliably down to Earth, you can provide something called base load power. Do we have any power engineers that wandered into the SATCOM class? No? It's a good thing to study, power engineering. You find that not all power is created equal. Like, solar cells are nice because even though they're intermittent, at least they partially match the demand, right? Like when people need air conditioning, that's when solar cells are usually at their peak optimum of performance, right? They're collecting sunlight because it got really hot, and you can use some of that extra capacity. Generally, though, renewable energies are really awful in terms of base load power, like wind power. That's the worst one. It always spins up in the morning and in the evening when you don't need it. And there's very little capability currently to store any mass energy on the energy grid. In fact, sometimes when you add those renewable forms of energy, it actually makes all the other forms of energy, particularly the coal and the natural gas plants, work less efficiently because they're always having to spin up and down at non-optimal times with non-optimal loading to account for the intermittency of these other renewable energy sources. So there's the nice thing about space solar power. The sun never sets in space. You get a constant stream of power, and that is the most valuable. Really only nuclear probably has a comparable base load provision. Nuclear plant, you turn it on and you have to shut it down maybe 1 week out of every year to service it. It's beautiful in terms of its base load provision. So anyway, people have thought this was a good idea for a long time, but they didn't see any particular way to do it efficiently. The godfather of wireless power transfer, Bill Brown, still has like the signature demonstration of this technology. It was actually an Earth-based demonstration, but he used NASA's Goldstone dish to transmit 34 kilowatts at over 80% efficiency at a microwave frequency, or almost microwave frequency, 2.4 gigahertz. And he did it for over a kilometer, just to show how you could do mass power transfer. And this is sort of the gold standard of wireless power experiments. In Kyoto in 1983, there's some researchers that launched suborbital rockets. So they just made sort of an arc really high, and they did some power beaming experiments to them. Georgia Tech, I always like to brag about some of my former students. They designed a 2019 satellite and launched it, which powered up with solar cells, made a microwave beam to a little rectenna farm here that harvested and did some scientific work, drove some sensors and some communication modules. In 2020, the U.S. Naval Research Laboratory launched a module that collected sunlight and then transmitted, I think it was 10 gigahertz on the other side. Tested that in space. Paul Jaffe, and U.S. Naval Research Lab researcher, did a 2020 experiment where they lit up what they call an lectenna, LED rectenna. So an antenna connected to rectifiers that turned RF into DC and lit up a little LED light. These are all real small experiments of wireless power transfer in space, but you got to start somewhere, right? Caltech just launched something at the end of last year. This is the biggest experiment to date, a 10 gigahertz wireless power transfer experiment. And they were also looking at a spacecraft that unfurled, that was very thin and low area density, and I'll talk about that in a second, and could collect power from that, but would roll up in a rocket fairing very efficiently. So there's a lot that has already been done, and here's some future demonstrations being planned. The Arachne program is the main thrust of probably several demonstrators coming out of the SSP IDR program that the Air Force is running. SSP IDR is Space Solar Power Incremental Demonstrator Research, I think. SPIDER, we call it for short. And so not surprisingly, Arachne was one of the satellites that the U.S. Air Force is planning to launch. It's going to have 10 gigahertz beamer and a solar panel to test beaming down to Earth. Georgia Tech actually has a little satellite on top of this. It's called WEBS. And I forget what the acronym is, but we're helping out. Professor Gunter over in aerospace developed that satellite. And not to be outdone, China claims it's going to launch an entire system in 2028. The UK says 2035. Japan always has a demonstrator available in N+2 years that it's going to run. And the European Space Agency just announced the Solaris project. I don't have firm deadlines for that, but this will be kind of similar to the Arachne experiment, where they'll be doing some space-to-space power beaming, space-to-Earth power beaming. Why? Why all the sudden interest in this? Well, I titled the talk over in Portugal, "The Space Solar Power Demonstration That We Actually Need." Because all of these experiments that I just showed you, past and present and future, are taking solar energy from space, turning it into DC power, and transmitting a detectable amount of RF energy on the Earth. Like every satellite since Sputnik almost. So what are we really demonstrating by doing all this? I'm not trying to be devil's advocate here, but how are we pushing the envelope by doing that? So my title of my talk was "The Space Solar Demo That We Actually Need." And I'm going to give you the specification for that. This is the demo that I think we actually need. And then I'll go back and explain why. And then we'll come back to this slide, and it'll make a lot more sense. But it's always nice to kind of know in your mind where we're going before we explain it. So, specification for the next space solar power demonstration. This is my dream proposal to you and to the world. This is what we actually need to get it to work. Launch 2 low area density satellites into space, preferably geostationary Earth orbit, that can perform station keeping with solar pressure rather than rocket fuel. and gets into a little bit of what we're looking at in homework number 2. Demonstrate that these spacecraft can transmit a sustained, mutually coherent RF beam to the surface of the Earth with over 1 kilometer of separation in space from one another using a secure pilot beam. We'll talk about that later. If you do that, in industry, we talk about, when we develop new systems, we talk about alphas and betas. Have you heard this term? Like, I just made the alpha prototype for this. And then you make a beta. Alphas and betas. Alphas, you're not selling alphas, and probably you don't sell betas either. But what you're trying to accomplish with each of those steps is philosophically different. Like, the alpha is supposed to demonstrate the technology, but it's not going to demonstrate all the scaling that you need to do it into the commercial marketplace. So maybe the first person that was designing one of these smartphones, they said, "I've got an alpha for you, Steve Jobs. Here's the alpha of the iPhone." And Steve Jobs probably came in, and there was a bunch of scopes and wires and antennas and spaghetti and maybe a little screen that you could fondle and twiddle. And they said, "Well, I can't solve it." Yes, but we proofed all the technology. We removed all of the uncertainty in the technology and the engineering and science behind the idea. I'll work on a beta that, even if it's not quite ready to manufacture, then it will look more like the final form factor, and we'll be able to template that and mass produce it and get it better at it and dominate sales for the next 15 years. So that's the kind of idea. This is the alpha that will remove all of the technical challenges that we face, and then it will give us sort of a clear path, still a ton of engineering work to be done, but a clear path to figure out how do we scale this up to a profitable production. Because in the end, that's what we want, right? Yes?
I have a very fundamental question about this.
I love those.
Is it safe to transmit such high power over space?
It depends. It depends. I'll give you some numbers. Ask me that at the end of the talk. Or if we leak into next week, ask me that. So there's our demonstrators. I'm going to go through a very simple calculation. This is sort of over the years how I've learned to think about this problem and to really think differently than a lot of people that work on this field. Because if you say, okay, this is a hopelessly complicated system. How do you cram the knowledge of a space solar power system, which involves all this astrodynamics we've been talking about, RF, high-powered RF, antennas, market prices for energy, rectenna electronics, land price. How do you wrap your head around something that complicated? So I'm going to break it down, and I'm going to let you think about it the way I think about it. If you tell somebody, okay, you're the microwave source guy. And we say, are you the I don't know, Andrew, are you? I mean, Skippy. Are you? What is your specialty in grad school?
Well, I like studying microwave.
Okay. So I smelled one. Smelled a fellow RF engineer. So he's going to build the best source. So he's going to look in a catalog. He's going to say, I'm going to build the best, most efficient, high-powered source. He's probably going to find like a magnetron or something, and he's going to build that system. And then, do we have any solar cell people here?
Right now.
Oh, okay, yeah, that's right. Dylan is my solar cell example person. I'm going to say, Dylan, I want design me a space solar power solar cell. And he's going to go through and he's going to find maybe the multi-layer with a concentrator, crystalline silicon, heterojunction solar cell that has like 45% efficiency in space, and it's going to be beautiful. He's going to hand that to me. And then, what are you studying? Antenna. That's great. He's going to say, give me a focusing antenna, a really nice, she's going to make a dish, and it's going to be coated in gold to keep the conductivity and the corrosion and everything low. It's going to be a nice thing. It's going to be very efficient, extremely high efficient radiation efficiency, like we studied last time. And so I'm going to take these systems together, and I'm going to put it on the scale. And I'm going to have a device, a spacecraft, that will likely have more than 100 kilograms per meter squared of area density. I'm talking basically the cross-sectional area divided into the total mass of the spacecraft. Just like every other spacecraft we've pretty much designed and flown into orbit. That's the order of magnitude that we're talking about. So let's think about things just a little bit differently. I am going to develop a notion of a profitability indicator. Like, will this system ever be profitable? Because ultimately, as engineers, that's what we have to answer. All the technology stuff is really to answer that question. And I'm going to call this profitability indicator number one, because it's the most important one and the most intimidating one. If this probability indicator is greater than 1, then we know we've at least covered the cost of launching the satellite infrastructure into space to do this. If it's less than 1, then we got to go back to the drawing board. If the probability indicator is greater than 1, that's not a guarantee that the system will be profitable, because there are other indicators that we have to bring into the picture. But this is the big one. If we can overcome this one, we're in business. So the revenue from total collected power divided by the cost to launch the spacecraft. That's going to be my first profitability indicator. How much revenue from the total collected power can I make? And here's how I would calculate that. I would take the collection area in meters squared, and that's basically the cross-section of the majority of the spacecraft that you deploy. It's going to be the solar cells. That area times the solar constant in space, so that's a constant, 1360 watts per meter squared, times the overall efficiency. And that's basically going to be how much of that can I actually bring down to the ground. So it's going to include solar conversion efficiency, generation of microwave signal efficiency, aperture collection on the ground, how good can I focus and collect it on the ground, and then the conversion back to some useful ground form. So all that's going to be lumped into one efficiency factor. The lifetime of the satellite, if I can send a satellite that lasts twice as long up there to collect power, then in terms of launch cost recovery, I've done twice as good economically. And then energy price, dollars per kilowatt hour. And for that, we have to use the wholesale price of energy, because that's what we're talking about. That's what we're competing against. So that's the top line. You can kind of see how the units work out. I have this fudge factor here for all the conversions that we'll get into in a minute. But you can see how you multiply all these together, and you get something that's going to be proportional to the revenue you can collect. Then cost to launch the spacecraft, that's spacecraft mass in kilograms, launch costs in dollars per kilogram. And I'm going to concentrate on this factor right here. I'm going to lump these two together because meters squared per kilogram, that's 1 over the area density of the spacecraft. That's how we define area density, as opposed to regular density, which is kilograms per meter cubed. Area density is kilograms per cross-sectional area. Okay. So now what I'm going to do, I'm going to take all of this constant and all the fudge factors to get the units to work out, and I'm going to put them in one magic value, which is approximately the number 12,000. And so this is what profitability indicator number 1 looks like. 12,000 times the efficiency of your system for collection end to end, years that the satellite will last in space, price of energy, divided by launch cost, divided by area density. And if I rearrange that in order to be profitable, I find that the area density must be less than this value right here. Yes?
So over here, does this expression also accommodate for the power that would be needed to keep the satellite in orbit?
Yes, so this will assume that you are using, we'll get to that in a second. There is some station keeping to be done, whether it's done through fuel or this other technique that I'll show you in a second. But That would either be extra station-keeping fuel that would show up in the weight of the satellite, which will influence your area density. Or we'll clarify that in a second. So let's just throw in some numbers. Let's just figure out how close are we today to making something like this economical. So efficiency, let's use a 20%. Now you figure out 40% solar cells, you lose half of it in the aperture. Our collection efficiency and generation are pretty, this might be a little rosy, maybe 0.15, but 0.2, we're engineers, we'll start with something round. Lifetime of a spacecraft, let's do 20 years. We did a really good job. 10 is on the short side, 20 is a little on the high side. We might be able to get 25 or 30. Let's just use 20. Price per kilowatt hour, 5 cents per kilowatt. That's a really competitive wholesale price in the United States where energy is cheaper than just about everywhere else. Launch cost, if we go to geostationary Earth orbit, because we want this thing to hang above a specific geographical load, we're not going to share it with like France and Iran and all this, there are the Caltech people want to do medium Earth orbit and then do some handoffs and some clever orbit design so that they're always dumping power in during peak times for the grid. Let's not do anything that complicated. Let's just stick with geo because it's hard. 5,000 kilograms to $5,000 per kilogram is Elon Musk's cheapest Falcon Heavy price to geostationary Earth orbit. So if we put all of these numbers together, you find that we get about 0.5 kilograms per meter squared for area density. How does that stack up? Does that seem achievable for a spacecraft? Well, let's see. I have this phone here, and I did a quick calculation. This phone has an area density, if I were to make a spacecraft by tiling it in a surface, you're going to have a area density of about 15 kilograms per meter squared, more or less. Different phones, different sizes, but that's a good ballpark. So it has less area density than a typical spacecraft that we launch, but it's still a lot heavier than we need to make it economical. However, this phone has a lot of mass to it that I don't need in space. It's got a lot of battery. I think most of the weight is in the battery and in the titanium housing for all the stupid things that I do to phones on planet Earth to protect me from myself. If you look at the individual circuit boards, you're getting pretty close to an area density of 0.5 kilograms per meter squared. And of course, these are coming down all the time. $5,000 per kilogram. There are some quotes that this could get down as low as $200 per kilogram when we get to mass launch, when all the efficiencies are taken into account. As we continue to whittle away at launch costs. So the point is, we are kind of within striking distance, but we have to kind of rethink about how we build satellites. Matthew, you have a question?
What's the current lowest area density of an optimal solar panel?
That's a really good question. The stuff they launch into space, they're always worried about efficiency, and it's usually based on crystalline silicon. And here's the other problem with space design. Space is expensive. Space is labor intensive. Y'all engineers, y'all are expensive. Your hours spent on something are expensive. And up until Starlink, we have never had to really mass produce satellites. So the mentality has always been, okay, I'm going to take an aluminum frame and take off-the-shelf components that are usually pretty bulky and space certify them, make sure that they can survive the radiation in space, and bolt them to this aluminum frame, throw it up. And so the solar cells are, I don't know the exact number, but I would say they're less than 10 kilograms per meter squared, but not much less than that. Sometimes a lot more. Depends on what chemistry you're using, what type of component you're using. And of course, you wind up bolting them to the big space frame that's pretty heavy and provides a lot of ballast. So the team that actually won the Best Paper Award for the Wireless in Space in Extreme Environments conference last week, they did a really cool study on something called a paddle sat. which is sort of a Georgia Tech innovation here. We're saying, well, what happens if the spacecraft becomes so thin that it becomes almost its own solar sail? So you have two flat discs on hinges, and you can imagine like a hinge here on this hinge joint. It also has a rotary axis, so that between the hinge and the rotor and maybe a very tiny little momentum wheel, doesn't have a lot of mass, so you can do 3-axis stabilization with a really, really tiny set of brushless motors. And you can pretty much orient the communication side of your paddle sat and your solar collection side, and maybe even want to silver the edge here, because the paddle sat is so low area density that in theory you should be able to do some basic station keeping operations using just solar pressure by changing the angle. In fact, you can even keep the solar panel facing the sun, and just through some modest deflections, add some momentum to the left or to the right, whatever you need over time to correct your orbit. So this is the architecture, and they did a really nice design and analysis on different control algorithms, like how much station keeping, or how deviant does the orbit get if you don't do any station keeping with this type of satellite in orbit, and then what happens if you dither your solar panel in different directions. How does that affect the power, and then how does that confine the spacecraft to a bounding box where it's supposed to be in orbit? And the idea is that you could fold these up, stack a huge section up, and put them in a rocket fairing and send hundreds of them out into space. So the other thing that's kind of neat about this, and this is really good for your homework because you're going to discover some of these same numbers if you do your homework correctly. If you're a conventional satellite, usually we neglect solar pressure. It doesn't really add something significant compared to all the other perturbations that exist on a satellite. However, once you drop below about 10 kilograms per meter square, it becomes a disturbance that you need to calculate. In fact, as you approach 1 kilogram per meter squared, you can actually do station keeping. If you get below 1 kilogram per meter squared, not only can you do station keeping, but you can even do some orbital transfer. It might take months, but you could imagine a paddle sat that, if the sun is coming this way, kind of orients itself with maximum cross section here. It absorbs and or reflects solar energy from the sun. So you're getting a boost during this part of the orbit, and then you kind of minimize your drag on the return. And in doing so, you spiral out to a higher orbit. And what's interesting is that, depending on your calculations, somewhere below 0.1 kilogram per meter squared, this type of satellite becomes completely unstable. It becomes very difficult to stabilize. It just kind of flies off with solar pressure, flings off into the great beyond, or you have to spend so much time deflecting that you don't really have any chance to collect solar energy from your paddle sat. So this is kind of an interesting phenomenon, and you'll be seeing some of these numbers on homework number 2, where you basically modify your little orbital simulator that you made in homework number 1 to see that you can take this into account. It's really not that hard. The hardest thing, though, is if you want to be realistic, the solar pressure will slowly vary in angle, right, as the Earth revolves around the sun. And so there's like a little bonus challenge to that homework, I think, if I remember correctly, that if you try to take that into account, you don't have to take that into account. You can just treat it all coming from one side. But if you try to take that into account, I'll be impressed, and I'll probably give you a couple extra points. So, now, why is all this important? Why are we trying so hard to minimize launch costs? Because in order to get to a bunch of infrastructure in space that beams down power, we really need to save money. Because you need a lot of infrastructure to do true focusing, especially if you want to do it in geostationary Earth orbit. So if you have an aperture in space and an aperture collecting transmitted power on the ground, let me switch over to the document camera just to show you what's going on here. So we're going to call this our space aperture. That's going to have a diameter d sub t. It's going to be r meters above the surface of the Earth, and you're going to collect down here at d sub r, diameter of the receiver. Here's your signal. And you're doing this at a wavelength of lambda. Then there is something called the diffraction limit, which represents the minimum amount of focusing that you can perform with a pair of antennas of this size. So the diffraction limit for this particular system would say I could capture most of the energy transmitted from aperture number 1 at the transmitter at this spot size d sub r on the ground if the product dr times d sub t is greater than the distance times the wavelength. If you transmit in the microwave frequency bands at either from 6 to 10 gigahertz, which is where most of these systems plan on operating, you can overcome most of the atmospheric effects with minimal loss. And the wavelength is going to be about this big. And if you're in geostationary Earth orbit, that means you'll have a little over a kilometer diameter on the ground, potentially up to a kilometer or so of diameter in space. So if that's a tremendous amount of stuff to put up into space. And the only way to make it economical is to make it very thin. And the nice thing about when you make it thin is that this launch cost, if you make it thin enough and can actually do some orbital transfer with the solar pressure, this now becomes $1,500 per kilogram. Because you only have to launch to low Earth orbit. You release all your paddle sats, and then they float out to geostationary Earth orbit. And I don't know if they operate as a fleet formation or if they assemble themselves into some giant infrastructure. It doesn't matter at that point how you do it. You've at least gotten everything to geostationary Earth orbit. And you have a transmission aperture that can beam down clean power to planet Earth at that point. So that becomes considerably lower, which really means that if you can make the area density less than about a kilogram per meter squared, you're starting to be in business. And we can imagine stuff like that. It has to change the way that we think about electronics and spacecraft, but one can certainly imagine an endpoint where you can make that type of economic spacecraft. Do you have a question?
Yeah, again, a basic question. So
Sure.
why is it that we've chosen millimeter waves? Because we're not looking to do communication, we're just looking to transfer energy.
That's right.
Why can't we do optical, like a much
Ah,
higher frequency?
yeah. So the problem with using anything other than like the lower end of the microwave band is that as soon as you go up above 10 gigahertz, you start to get into some serious atmospheric absorption. Even a few dB is significant, right? Because this is a power link, and it'll hamper the transmission. You also get into weather-related effects. If the rain or the clouds come over, optical, that will get blocked. It will add a lot of dB to the loss of something over 10 gigahertz. And then you lose the really valuable aspect of this, that base load provision capability. There are some situations, though. For example, people are talking about wireless power transfer of this type to power things like rovers and sensors and a little colony of scientists on Mars, or one of those lunar bases with robots floating around and investigating mines and that sort of thing. Water sources, and all the things that we talk about when we talk about moon bases. In those scenarios, jacking it up, because you don't have to go through an atmosphere, really. Mars, the atmosphere is only 1% the thickness of Earth. Doesn't matter what it's made of. It hardly absorbs anything. The moon doesn't have any atmosphere that we can detect other than a few blips of krypton or argon, I think. And so in those scenarios, millimeter waves and sometimes even optical lasers make the most sense.
But do we have the hardware to achieve that?
We have alphas that can transmit a lot of power at those frequencies, but we've never integrated them into a system economically.
Okay.
For the paddle set, the best way to approach that might be more distributed electronics, like little 1-watt transmitters distributed across a surface that are synchronized. It's easy to imagine what that would look like, but we don't have the processes in place to build that at a mass scale cheaply. You're talking about wide area processing. We have a lot of people that are working on that at Georgia Tech right now, sometimes in completely different contexts from this. So anyway, let's go ahead and revisit the specification. Launch 2 area density satellites into low area density satellites into geostationary Earth orbit that can perform station keeping with solar pressure rather than rocket fuel. They can stay 1 kilometer apart and maintain stable orbits. Demonstrate that these spacecraft can transmit a sustained, mutually coherent signal to one spot on the ground over time. And that usually requires something called a pilot beam, which is probably a source from the ground and at least 1 or 2 relays up in space, so that you can make for minor adjustments in the phase and the positional offsets of the transmitters. Easy to say, but nobody's ever really done that at that scale. It's physically possible. It really is up to the engineers to make it technically feasible, economically feasible. But if you can show that those two can be coherent, if you show these two components, then obviously there must be a way to scale it to a larger aperture across 1 kilometer plus in space, which is why this is such a stepping stone demonstrator for the technology. So does anyone have any questions? Yes?
So why do we need coherent transmission? Because can't we just take the energy from each of them separately and then kind of do something after that?
So the problem is, to get true focusing, you have to have coherence across that entire transmit aperture. If you break it into segments and just say, I'm going to have this segment transmit down, I'm going to have this segment transmit down, instead of focusing at the spot, what you will get is those individual little antennas will have much broader area beams, and then you'll basically just get constructive and destructive interference across the entire much larger swath of area.
So these are multiple antennas on the same...
Yes, that's right. Ideally,
okay.
You want a solid aperture. Everything is radiating down in phase so that this, and everything in between, when you add the components up, they perfectly constructively interfere here. And that way, as you move over to the edge, this pathway gets a little bit longer, this gets a little bit shorter, and at some point they're going to start to destructively interfere. And that's really what the diffraction limit tells you, is beyond a certain point d sub r, they're going to start to destructively interfere and you're not going to collect anything of substance. Yeah, Matthew.
So how accurate can we station keep in orbit? Because my question would be, if we're going to have to make sure that these guys are precise locations in space,
yes,
that they destructively interfere, we first need to make sure we can accurately keep them at those precise locations.
We cannot accurately keep them at that precise of a location, but we can, through cleverness, measure and electronically compensate in phase for positional offsets. Mm. But that's easier said than done. We can do that for millimeter scale positional offsets, especially in space where it's fairly open. But we've never done it in space at this scale, which is why the demo is so important. Yeah, very good intuitive question. Yes?
So this may not be like an actual problem, but what's stopping someone else from stealing the energy on Earth? like intercepting the signal?
That's a great question. So stealing the energy, usually this thing is going to park up in geostationary Earth orbit, and it's going to have a target down on Earth. So to steal the energy, somebody would have to like run out over here in front of the rectenna. And by the way, somebody asked earlier, what's the energy density of RF coming down here? Probably about 250 watts per meter squared. There's just some design, but that's not terrible. Like most of that RF would bounce off of you if you did decide to run out there and steal energy with an antenna. And keep in mind that, you know, if you walk outside with your shirt off on a sunny day at noon, you're getting almost 1,000 watts per meter squared of sunlight. Much of it ionizing, so it's much more dangerous than the RF.
So it would be possible to tamper with the antenna on space to change its trajectory.
It would not be possible to tamper it necessarily. What it would be possible, and this is the part that you'll notice in the specification, the word secure. What you could do is, people don't realize it is very difficult to cohere even the 250 watts per meter squared or so on the ground at a target. So, you know, some people think, oh, death ray, you know, like, what if we were to, like, I don't know, find an enemy? What if we were like have this constellation of satellites float over to top of Russia and like aim it to Moscow? They would have slightly warmer streets. The ice would melt a little bit. You probably wouldn't even notice. So it is not like and that's if you have the Goldilocks scenario where you've got pilot beams coming from Moscow and some relay satellites that can position everything right. The thing that I worry about is in order for this to be effective as a green energy source, you have to become reliant on it to at least a partial degree. Can we make a system robust enough in communication so that if somebody floats an adversary, not naming any countries, but an adversary floats a little satellite here and then jams the pilot beams, can you decohere the power and knock out power over a site for a little while? I think that's the real danger, the highest risk danger.
To make this, I guess, actually provide a lot of power for houses and cities, how massive would the array have to be?
Well, let's see. If it was, let's do a little calculation here. Let's say you had a 1,300 meter times pi. So it'd be like 1,300 meters would be 5 million meters squared times 1,360. So we're talking about you could get over a gigawatt down to the Earth under these kind of rough numbers, which is significant. That's a significant portion of what the city of Atlanta uses, or the metropolitan area.
And that's just with a transmit aperture of 1 kilometer?
Yeah, 1.3 kilometer. Times like a 0.2 efficiency factor to get all the way down. That one probably more like 0.15, 0.12. Yeah.
With someone, a user that's not like commercial, like in the military, who don't care about profit, who rather care about like using this system to take the battleground, like fight anywhere and have power anywhere they fight at, would they even care about profitability?
They would care about profitability, but obviously in that scenario, this number goes really high, the P, right? If P gets really big, then you can tolerate a more conventional spacecraft. And people have talked about that as like a forward operating base. You go to a place that you're not used to dealing with, and you have to power that system. And I forget what the costs are for, like, you know, providing power per kilowatt hour in Iraq or Afghanistan or one of these far off places that the military operates. It winds up being like tens or hundreds of dollars per kilowatt hour. So that's, I think Paul Jaffe, the guy I mentioned earlier, has some really good studies on those types of situations.